An Nginx microcache is a simple server-side cache that allows us to store dynamic language responses in order to avoid, or at least minimize, server-side language processing. For websites relying heavily on server-side languages and database access, such as PHP and MySQL, this cache can provide incredible performance benefits and drastically reduce server load. Simply put then, let's say a user makes a request for dynamic content. Nginx passes that request to PHP FPM in our case, which processes it and possibly even includes some database queries. PHP FPM then returns that processed response to Nginx, most likely in the form of HTML, at which point Nginx, using a microcache, can write that response to disk, meaning next time a user makes the same request, there's no need at all to even contact PHP FPM. The response can be read from disk, as with any other static resource, and sent to the client. Of course, it's not always going to be quite this straightforward, as dynamic content is dynamic for a reason. But in this lesson, we'll see how to configure a microcache for PHP, using Nginx's FastCGI cache. As before, I'll clear some of this previous lesson's code, remove all of the gzip directives, and the static resource location implementing gzip. Then, to enable and configure FastCGI caching in the HTTP context, making this available to all our server contexts, start by setting FastCGI cache path, which, as the name suggests, takes a file system location to which these cache entries can be written. I prefer to use the /tmp directory for this, as it gets emptied on boot for most Linux distributions, but feel free to create this cache elsewhere should you wish. /nginx_cache. Then, on the same directive, add a parameter called levels, setting that to 1:2, like so. Now, the levels parameter is a very poorly documented parameter, but essentially what it allows us to configure is the depth of directories to split the cache entries into. If you leave this out, Nginx will simply write every cache entry directly to this cache path directory, which is fine for smaller sites. But setting it to this means storing the cache entry in a directory equal to one character off the end of the cache entry name, and then again in another directory equal to 2 characters off the end of the cache entry name, and so on. This cache entry name we'll discuss in a second, but it will look something like this. Next, still on this directive, add another parameter, keys_zone, equals the name of this cache. This can be any descriptive name you choose, for example, my cache, or zone1, etc., followed by a colon character and the size of this cache zone, 100 megabytes, which should be ample for most sites. And finally, an optional parameter, inactive, which sets how long to keep a cache entry after the last time it's accessed. This defaults to 10 minutes if omitted, but I'll up it to 60 minutes. That's all I'll set on the cache path directive, although a number more optional parameters does exist, these just being the key ones. The second directive we need to configure our cache is FastCGI_cache key, a standard directive that takes a string format from which to create cache entries. For example, I'll make this a very common format of scheme, so HTTP or HTTPS, request method, get, post, etc., host, the domain, and request URI, meaning a typical cache entry will be identified as, for example, https get domain.com/blog/article. This being the way Nginx identifies a request to a cache entry. So, let's say your entire website is accessible over both HTTP and HTTPS, no changes whatsoever. You could leave out the scheme variable to have both http domain.com/blog/article and https domain.com/blog/article served from the same cache entry, whereas adding the scheme, as we did, will create two entries, one for HTTP and one for HTTPS. An important concept to understand. Generally though, going with this format is a safe, albeit overly specific format. Another important point to mention in regards to this cache key format is that this string is hashed, or more specifically MD5 hashed, to create the entry name I referenced earlier when setting the levels. Okay, that's our microcache configured. Next then we have to implement this where we want dynamic content to be cached. In our case being this PHP location, where to enable caching we can say FastCGI cache zone 1, the cache name or identifier. And secondly, to fine-tune the validity of these cache responses, we can also add FastCGI cache valid, and then specify how long a cache response should be valid for, based on the response code, or multiple codes, 200s and 404s for example, is valid for 60 minutes, as per this value here. Or alternatively, this being an array directive, set 404s to only be valid for 10 minutes, and so on. I'll stick with 200s for now. Save this, and before I reload the configuration, let's test the current performance without our new microcache. Now, to test this, we can use a number of tools, but the simplest and preferred one for me is Apache Bench, a simple HTTP benchmarking tool from the Apache organization. To install Apache Bench, run apt-get install apache2 utils. Or if you're using yum on CentOS, you can do the same by running yum install httpd tools. That's all done. Check we have the tool available, AB being the Apache Bench command, and there we get the help output. So this is ready. At the moment we only have that default index.php request available, which if I curl it, gives us this HTML heading with the date. Not the best example as there's hardly anything for PHP FPM to process, but nonetheless, we'll test this by creating 100 requests to this page in lots of 10. So 10 connections at a time, 10 times. Using Apache Bench then, we can do this by running AB with an N flag, 100 for 100 requests, C flag, 10, meaning with a concurrency of 10 connections to that IP. Enter and done. The two most significant numbers here being this 1662 requests per second and the average time a single request took to receive a response. Also keep in mind that this test was run on the host server, so providing an even faster response. But we can change this. I'll open that index.php file for editing, /sites/demo/index.php. And right before the script response, I'll add a 1-second sleep. So basically simulating a long-running process like a database request or even a large loop, etc. Write that out, exit the editor, and now when I run this test again, we should get a drastically slower test. I'll skip through the waiting, and there. We're down from 1662 requests per second to only 4.6, with the average time per request being 2 seconds. Those concurrent connections already backing each other up then. Meaning that on a typical request like this, Nginx can now cache the first response and then serve the remaining 99 from that cache almost immediately. So let's see that. I'll reload this configuration, enabling our new microcache. Same test again. Done. Even faster than the first test without the sleep function, at 2550 requests per second and only 3.9 milliseconds on average per request. A massive increase in server performance then, with the added benefit of the server not having to use nearly as many resources. At the moment, however, we still have no way other than these really fast response times to know whether the request was actually served from the cache. Luckily, the FastCGI cache module allows us to check the status of a response, meaning whether it was served from cache or not, by means of a variable, upstream cache status, which we can pass with the response as a header. We'll add this to all responses, so in the HTTP context, say add header, I'll call this X cache, X being a naming convention for custom headers, upstream cache status. Save this, reload the configuration, and now do a curl request for the headers. Enter, and there we have it. X cache hit, meaning this was served from the cache. So to see a cache miss, we can simply change the URL, making it explicit by adding index.php. So same request, but remember that FastCGI cache key format, it includes the request URI, meaning this is now a new cache entry. Enter, and as expected, miss. The last important part of dynamic content caching is adding cache exceptions. First, let's create a variable with which to track cache exceptions, starting by default with no exceptions, so just cache. Set, call this variable noCache, 0. Then, as an example condition, add an if statement, a very common condition on which to disable caching being if the request method is a post request, meaning a form submission, etc., or for the sake of demonstrating here, if a query parameter $arg with the name skip cache is 1, set noCache to 1, or in other words, true. Then to actually have caching disabled on the condition of this variable being 0 or 1, in the cached location, set FastCGI cache bypass to the value of the noCache variable. And the same for FastCGI noCache. Meaning if this variable is 1, bypass serving this from the cache and don't write the response to the cache either. Save this, and now we should be able to completely bypass the cache by setting the skip cache query parameter to 1 on any PHP request. Over to the terminal, reload, curl as before to ensure we get a hit. There it is. Add the skip cache query, however, and this time we get an explicit bypass of the cache. So an easy way to add exceptions for anything like logged in areas of your site, live data, etc. That's where we'll leave microcaching, but be sure to have a good understanding of this lesson from start to finish, as caching server-side content will be the single biggest performance enhancement you can add to your site, given you serve dynamic content or handle many generic database queries.